it looks like elements that are breaking down, essentially. It looks like chemistry, actually.
Yes, exactly. Yeah, exactly. And that's one of the things that I love about geology is that there's so much chemistry layered in it. There's so much physics layered in it. There's every other science is layered into understanding what's actually going on with the planet.
Welcome to Wonder, brought to you by Geo Co. I'm Holly Cooke, joined by my colleague Dr Reid and the Geo superstar Dr Sandra McLaren, former university academic, all-round incredible geologist to talk to. Today, we look around at our solar system. We look at the relatively stagnant, dead planets of Mars and Venus, and then we cast a light on our own, ever-changing, colourful, always busy, and we wonder what makes Earth so special, so alive, and always changing. And that, I think, lies in heat. But let's get into it and we'll delve into the curiosities of our hot planet. Sandra and Anthony, let's strap on some jetpacks. We'll launch ourselves into outer space and we're going to turn around and look at our pale blue dot. And if we had a time machine button that took us back 50 million years ago, we wouldn't see the Himalayas. They haven't grown yet. If we went back 500 million years ago, we'd actually see this big supercontinent Gondwana. We'd see not the Atlantic Ocean, not the Pacific Ocean. We'd see the Tethys Ocean. Back even further, we would have oceans of magma.
Well, a long time ago.
Like billions of years ago. But then if we peer around to Venus, we peer around to Mars, and we see comparatively still, static, dead planets. So my question, Sandra, is why on earth is Earth so different?
Oh, Earth is just so beautifully special in the sense of what's in the solar system. And because exactly as you say, Holly, that when you're looking at the adjacent planets, doesn't seem to be much going on. And yes, we do have scientific debates and observations are constantly being made to see exactly what's going on. But you certainly don't see the signs of the dynamism that we see on Earth. So mountains, so the fact that we have mountains on Earth means that there's something must be happening that's transient, that's changing, because otherwise you'd just be flat everywhere. It'd be so boring. Nothing would happen. We'd get none of the cool stuff that we A, depend on to live, and B, is really lovely to see. So, we are very special. Earth is a very special planet, and there's one key reason for that, and that's the heat that's still contained within the Earth. So what all that the Earth is doing at its surface, and it's right the way through to the very innermost part of the core, is happening because the Earth is hot inside. It's a bit like if you cook a pudding or a cake or something like that, and
hungry.
it stays hot on the inside for quite a long time, even though it starts to cool quickly on the outside. And it wants to cool down because the solar space is cold. So you've got this hot body sitting in this cold medium, and naturally it's going to cool, but it takes a long time for that to happen.
Wow, that's such a good explanation of that.
So Earth just wants to cool. It's a simple thing.
I'm still thinking about the pudding. So in a pudding, they often talk about the crust on the outside of the pudding, or on a bread loaf or something like that. We talk about the crust in geology too, don't we?
Yeah,
I see where this is going.
We do. And sometimes we have a molten, if you've got a really cool pudding, it's got a molten caramelly bit in the middle or something like that, and we might have something like that similar, analogous in the Earth as well. So we do use that word crust, and I'm sure that's where it originally came from, because people made observations of their everyday objects, and so much of what we see in geology can be related to processes and phenomena and things that we see every day. So a crust is the hard layer on the edge of your pudding or your cake or whatever it might be, and we have exactly that on the Earth. So it's slightly more complicated in some of the words we use, but essentially that's just the hard layer that's on the outside. And inside it's still hot and it's still cool.
It's not like completely liquid. Like I'm still picturing that pudding when you cut into it. I'm getting really hungry already. Okay. Anyway, it's not liquid in the middle of the Earth, right?
There is some layers of the inner part of the outer part of the core where people still think that it is liquid. However, and I'm not totally up with the research, because I know that seismologists are incredibly cool people. I'm always in awe of seismologists. So they can see inside.
So brainy.
So smart. So they can see how waves go through the interior of the Earth, and they can tell what's solid and what's liquid and what the densities are, and it's so cool. And there's been some new research come out of Canberra recently about what's happening in the core. But certainly there's a bit of a person on the street might imagine that the interior of the Earth is just this molten mess of the sort of stuff you see when you see those cool videos of Iceland when the volcano sets off. But that's such a tiny, 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 tiny proportion of the total volume of what's inside. Most of it is hard rock. It just happens to be hot. but not melted.
Yeah. So we're saying that the rise and fall of mountains, the opening and closing of oceans can all be traced back to the Earth just trying to shed its heat.
Exactly.
But how?
How does that happen? Yes.
Please help me understand.
Yeah, really good question, Holly, because it's kind of like it's very difficult to visualize. So, what's happened? So it's very hot in the inside of the Earth, and where is the heat coming from is the other big question that you might want to say. It's like, why is it hot in there?
Yeah.
I mean, what are you telling me this, falsehood for? But it's hot because there's a couple of sources of heat. First of all, when all the planets were made, how we went boop, 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 and coagulated into a planet, all the kinetic energy that those asteroidy bits and whatever else had gets converted to heat when it gets amalgamated in that proto-planet. And then there's a secondary source of heat that is happening and being produced from the radiogenic decay of all sorts of different radiogenic elements.
Right.
And in the early stages of the Earth, there was a lot more of those than we have now. So when the atom decays, it releases heat, and then that heat's got to go somewhere. So that heats up the local area, and you could basically have two sources of heat energy.
So that first one is actually the physical compaction and interaction of protoplanetary debris.
Exactly, yeah.
Is still contained in the centre of the Earth.
Yes, that's right. And people do debate how much of the heat is coming from that and how much is coming from the decay of the different radiogenic isotopes. And there's debates on this all the time. And it's
Are there?
A bit tricky to know what the proportions from each of those things are.
You said the radioactive isotopes decay over time.
Yes.
So can we calculate how much there was at the start? Is that something that people can do?
Yes, people can do that, and they have done that, and we can see how much has decayed, which is quite a lot over time. So it sort of makes your mind boggle as well, what was happening on the surface of protoplanet Earth really, really early on, soon after it was formed. And people debate what happens there and what sort of evidence do we have of those processes and so on. Now there's really only three elements, 4 isotopes that produce significant heat that we can measure on a geological timescale, and that's potassium, uranium, and thorium. But early on there was others, including aluminium, if I remember that correctly.
Alfoil.
Well, yeah, sort of, yeah.
Yes.
But radioactive aluminium, I think it was 26, but don't quote me on that. Decay had a very short half-life, so it lost all its heat really quite quickly, whereas the isotopes we're still looking at now, uranium, thorium, potassium, have really long half-lives. So they're still ticking away and still producing the heat.
That's a key point. I don't think I appreciated this. That's the lie. I still don't really appreciate it. But that's what the heat sort of looks like. It looks like elements that are breaking down, essentially. It looks like chemistry, actually.
Yes, exactly. Yeah, exactly. And that's one of the things that I love about geology is that there's so much chemistry layered in it. There's so much physics layered in it. There's every other science is layered into understanding what's actually going on with the planet and how we live on it. And I just think that's the coolest thing ever.
Was chemistry a bit of a window into geology for you?
Yes and no. Yeah, I found the chemistry that I learnt was very very narrow, and the chemistry I learnt wasn't particularly applied to other things. Whereas when I did geology, like by mistake, as many of us do,
just stumbled into the wrong lecture theatre one day.
I did. It was a very happy accident because
how common is that though? I mean, that's such a common thing for geologists. There's everyone's I did it by accident, or I loved the field trips or something like that.
And I loved what I could do with my chemistry and my physics and my maths, and that's what I saw where I saw it all coming together. And I'm like, hey, I can explain this, and this that I can see, and I can make sense of things. So there's a lot of chemistry in geology. There's a lot of physics in geology, but this earlier stuff is a lot of chemistry and a lot of physics, which is very cool.
I relate to that point, just to digress for a second, where I grew up on nature documentaries and all these physicists. I idolize these physicists. But now what I do when I watch those documentaries, I'm like shouting at the TV screen, like, that's geology, get that out of a physics documentary. And I sort of have this idea of it's all these sciences come together, but you often see other disciplines taking on the earth sciences.
Yes, without
saying it's earth science.
Exactly.
Not fair.
Yeah, pretty much. No. Goodness me. So we had asteroids smashing into each other way back when, and that heat is still to a certain
trapped in a sense, right?
Yes, exactly.
Is that because rocks don't conduct heat very well?
Rocks are not too bad at conducting heat, but they're not the best, obviously. Something like a pure metal bar or something is a brilliant conductor, your silicon or things that you have at home.
Yep.
but they are pretty good. And some rocks are much better at conducting heat than others. But there's an even better way of moving heat around that's not relating to conduction, and that's convection or advection of heat. So physically moving things is the most efficient way to move the heat around. And so if you want to get the heat, or the Earth wants to get the heat from inside out to the edge, the best way for it to do that most efficiently is to melt something or move something up to the edge, and then the heat gets lost out of the surface. So two main ways that we move heat around: conduction, convection. Convection is much more efficient, but conduction is what mostly happens.
This is throwing me back to my 3rd year classes. Like, we talk about mantle convection. Can I just say that word and then push it over to you?
Yeah,
please tell it.
Definitely. So we might start with mantle. So Anthony's already mentioned the crust. So the crust is the rigid outer layer of the Earth, and typically it's only about 35 or so kilometres thick, which sounds like a lot, but when you think of the radius of the Earth,
nothing.
It's basically nothing. And there's a really good analogy you can do at home. You can get an egg, you can boil the egg, and you can slice the egg open, and you can have a look at how thick the shell is with respect to the rest of the egg, and it's kind of about the same ratio of crust to the rest of the Earth. So crust on the very outside, and then the next layer, which is the most volumetric layer of all of the bits of the inside of the Earth, is what we call the mantle. Don't really know the origin of that name. I should look that up. From? Yeah, I think it's because it's something on the outside of something else, being the core. I'm not sure. Good question, though. Yep. Should probably know that. So the mantle is the main volumetric layer, and is made up mostly of a rock which we call peridotite that contains really cool minerals like olivine and garnet.
Olivine.
Olivine is the most beautiful
green.
One of the most beautiful. Garnet is the most beautiful. Let's talk about. No, that's not.
That sounds like
another day.
Yeah, another day.
But olivine.
I interrupt the transmission to say that it's Old English, Latin, whatever, but cloak. The cloak.
The cloak.
Is the cloak. It's quite lovely.
Yeah, well, like
cloaking the core, maybe.
Yeah, exactly. Yeah, that's probably right.
Anyway, but just on olivine, that means so the mantle isn't some liquid, oozy-goozy thing. It's just sounding pretty solid.
It is very solid. And again, that's one of the things that if you talk to people, they think, the inside of the Earth is just this molten, gloopy mess that's just sloshing around. But, it's very solid. It does move on geological time, though, because it's hot enough to move. So when something gets hot, it gets less dense. So if you've got a hot air balloon, we all know how they work. You heat up the air, and that's why your hot air balloon goes up. So it's essentially what we're doing to the rocks in the mantle. The core is very hot, and some bits may be molten, as we talked about before. So that's hot, and that heat goes up and out. And so it heats up the rocks in the mantle, and some of them get warm enough to start to move like your hot air balloon, and they just slowly go up. And then everything else above that has to move out of its way. So this is a way in which we initiate these convection cells, which we can visualize and image beautifully inside the mantle. And they're so amazingly complicated because, of course, the Earth is a 3D object, not a 2D slice. So we've got convection coming up and cooler bits dropping down in 3 dimensions, and the patterns are just gorgeous. So, but that's a very efficient way of moving that heat up and out.
What's the sort of time frame that those things happen over? Like, if you imagine like a piece of rock right at the bottom, and it's trying to work its way up, does that take?
That takes
hundreds
of millions
of years.
Couple of hundreds. If you're coming right from the base of the mantle, I guess it would be a couple of 100 million years. Yeah. I think you could calculate it.
You could. I'm sure you could calculate it. I don't think I could calculate it.
I'm sure you could. In part, also depends how fast we're getting rid of it at the top as well, because it's like a push-pull thing. So the hot air is pushing up, but then if you've got cold, not hot air. I said hot air. I'm
still full of hot air.
Yeah. I'm still on my hot air balloon analogy. The hot rock comes up, but then the colder rock up here is more dense, so it starts to drop down. So if that's dropping down quickly, this can help move up. So it's one of those.
So they're kind of connected.
Linked, exactly. Yeah, exactly.
Because they're just all a series of minerals basically touching each other, right?
Exactly, and you've got a thermal gradient, so a change in the temperature, and that's going to always keep promoting this convection, where as long as you have that change in difference in temperature, you're always going to get that movement of those rocks.
So I've got a question for you. Olivine, from if I can remember rightly, is mainly comprised magnesium and silica and maybe a bit of calcium,
iron,
I think,
but
no potassium. Details.
Yes, no.
No, but basically the point of that question is there's no potassium in it.
No.
There's no uranium in it.
No.
And there's no thorium in it.
Good question.
This is where I was thinking too.
So what?
What's the heat?
What? How does those two sources of heat interact?
Yeah, no, really fantastic question, and it relates very much to. So we see what we've already talked about: crust, mantle, and then the core, which we haven't really spoken about. Then is a compositional layering, and that there's very different rock types in each of those three places. There's also a thermal layering there as well, as we've talked about, and that means that we have a rheological layering, which means a fancy dancy word for how things behave when they're squished or stretched.
Right.
Anyway, I digressed.
So as you go down through the Earth, there's both changes in chemistry as well as changes in temperature.
Yes, that's right.
And both of those things affect how strong rocks are, right?
Exactly. So how easily they can move in that convection cell, or how easily over millions of
years. Just to clarify.
Yeah, it's not happening.
I think that's the great thing about this, though, is that we talk about this and sort of we can kind of visualize it, but this is incredibly slow processes.
Yeah, incredibly.
Some of them are incredibly slow processes. Obviously, the eruption of the Icelandic volcanoes will happen quite quickly.
But this is the beauty of it, isn't it? We have snapshots of the Earth being built, and then we have, oh my God, it's taking forever, the Earth being built. And both are really important.
And both are valid and perfectly true. Yeah, exactly. Yeah. But things like Iceland today are kind of snapshots of what might have happened really early on, because that compositional layering wasn't always there. And the compositional layering, as you've alluded to, is really quite strong between those Olivine rocks and the rocks of the crust, which are the ones that have almost all of the potassium, uranium and thorium and various other.
So, but that's only the outer kind of middle shell. That's where all those radiogenic or radioactive minerals, elements are sitting, right?
Yes, exactly. That's right. And why is that? You might be your next question.
That was my next question. I'm sure Holly was just about to ask that too.
Yeah, in my mind, I'm just like doing the clunkiest joining of dots. So we've got this early Earth asteroid smashed together heat powering this like massive but very slow mantle convection. We've learned that the mantle isn't oozy-goozy liquid. It's solid. It's comprised of this weird mineral that we're calling olivine. Yeah. But then we have this secondary source of heat. We have another source of heat that we're talking about, but that's not deep that's not deep down. That's just sitting on the eggshell of the crust, but it's equally as important.
Yeah, and it's much, I guess, more important when we start to look at individual geological processes like building a mountain range or producing a basin.
That happens on the surface.
Like that. That's right. So they're both important, but they're important on different length scales and different time scales and so on. So yes, by far the majority of that radiogenic heat is in the crust, and that is because very, very early on in the Earth, we did have a lot more heat, as we've already talked about. So rocks were melting. And when we melted that early Earth, there's some elements that go, don't like this, I'm out of here as soon as the temperature gets hot enough and the melt forms. So if you think about,
so do you mean those elements will go into the melt?
Yes, they'll go into the melt and they're hot,
happy to go away.
Exactly. And because the melt is hot, as we said before with my hot air balloon analogy, it's buoyant, so it's going to rise up. So that melt will take out anything in the source region that is what geochemists call incompatible. So they don't like to be there. If there's a melt, I'm off. I'm out. The bus is gone and I'm taking
the first
off.
Ticket. Yeah, exactly. The first plane ticket out of here.
Ticket out.
I'm going to the crust.
Exactly. And that's exactly what happened volumetrically across.
I'm so sick of the pressure down here in the mantle.
Exactly. He's on fire.
Exactly.
I need a holiday in the crust.
Too stressful. I need to go. Yeah.
So they jump out of their source regions, they jump out of the mantle, and then they blub 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 up.
They come to the crust. That's how we think the crust originally formed. A lot of other layers of processing there. But yeah, there's this, and we think that happened pretty quickly actually, from that glue our protoplanets together, was homogeneous, but now we've got this really strong layering, which you've mentioned, and that we think actually happened pretty quick, because those elements they're not going to hang around waiting for the next bus. If this one, they're just off. They're off. Yeah. And then that.
I'm just picturing little potassium sitting there, like, first chance I get, I'm out of here.
Exactly. Yeah.
I'm going to ask a question.
I hate olivine. They're mean to me.
Oh, okay. I like olivine, and it's a green color. I have a question, and this is going to be hilarious because I'm not confident any of us can answer it. But when we started out with saying that, why is the Earth so special? Yes. Why is it so different? Why is it always changing its face? And then we look around at other dead planets. Yeah. This layering feels like a pretty fundamental process in all of that. Do we know if the other planets are layered like this?
Ooh. Sandra?
Or is this an Earth thing? It's awesome if we don't know the answer.
Oh, let's find out.
We'll come back on the next episode with an answer.
Yeah.
But there you go.
I believe there is some layering, but we don't have as many observations as we do, because here we can put our seismometers down and we can see quite clearly. And I'm pretty sure you might know whether or not you can do that on other planets. And I don't know that we necessarily have that.
Well, it can be done, and they have done that on the moon.
Yeah.
The Apollo mission did put out seismometers and measure it.
And it's pretty. What's the moon? Is the moon pretty?
It's got something. It's got something in the middle,
Something.
which is hard and sort of denser than the surrounding.
Yeah.
But there's a lot of uncertainty in that. Those measurements were taken in the 1970s with not perfectly kind of, I guess, modern, if you like, seismic instruments now. So there's a lot of work that are going to be happening on the moon for that, and the same for Mars eventually.
We'll put a pin in it.
Yeah.
All right, next left field question. Here we go. We've recently been chatting to some geos who made their way to Antarctica to check out the Denman Glacier.
Yeah.
And I'm reaching far in the back of my mind, and I think it was Jackie Halpin mentioned that there was some hot rocks underneath Antarctica, which was making everything melt faster.
Yep.
Does this feel related to what we're talking about?
It is, Holly, exactly. And that's there's so many cool things to see and understand. And the geological record down there is just so amazing to be able to read and understand. And it's kind of a really nice analogy to what we see on the Earth as well, because you've got a glacier that's just sitting on top of the Earth and then sitting on top of the crust in this case. And that's where all the uranium, thorium, and potassium is. And that's still ticking away with its radiogenic decay chain. And so it's still producing heat. So you've got your glacier and you've kind of got a Bunsen burner underneath it. Not
literally a Bunsen burner.
Maybe an electric blanket on low. Yeah.
I just think next time I go and sit on a granite, it's going to be...
You're going to get a warm bottom. Not quite. I've sat on lots of granite.
You'll be fine. You'll be fine.
But it turned down way scale-wise. It's like putting your ice on top of a low electric blanket. And so what's that heat going to do to that ice? It's going to start to melt the bottom of that. And that happens everywhere, and that's a perfectly natural, normal process. And there's heat coming through the floor here where we are recording. There's heat coming through everywhere. And we can measure that, and we can measure the total amount of Earth heat that's coming out of the Earth if we integrate all those observations globally. But yeah, absolutely. There's some special rocks down in Antarctica, of which there are also some really special analogous rocks here in South Australia, where all good things are, that are really, really enriched in those radiogenic elements, uranium, thorium, and potassium. So they're sitting there. They're a bit hotter than normal. So we've turned our hot electric blanket up slightly hotter. Mm-hmm. So we need to understand the effect of those on the materials above. Yeah.
So how much spatial variation in that heat is there? Like from granite to granite, like if we went to a granite in the south of France or a granite in...
Wouldn't mind that. Yeah. That's all right. All right.
I'm trying to get us back to food here, food and wine. Yeah. But anyway, as opposed to a granite somewhere else in the snowy mountains.
For example, yeah.
Arkaroola. How much variation is there?
There's a lot of variation within a fairly well-defined range. So, but if you walk sort of like a few hundred meters across Arkaroola, you'll go from a really hot rock to might walk into the adjacent sandstone or something, and that's got basically nothing. You might go to the next granite, and it might be slightly older or slightly younger, depending on the case. So therefore, it is likely to have been produced from a different melt bus, if you like, which we were talking before.
That's so good.
I really like
the melt bus. Get on the melt bus. Yeah, that's good.
Going. Yeah. And so it may have a different amount. So there's quite a lot of variation.
There's a lot of variation, isn't there?
Yeah.
And because we see different rock types, basically wherever you stop your car and hop out on the roadside, you normally see a different rock to the one you've seen before, unless you're driving along parallel to something.
Yes.
But if you're going across things, then you often see a lot of variation. So those rock types all have different budget or different amount of heat producing elements.
And certainly granites have the highest on average of the different rock types that we've got because of the melt bus, whereas things that are sandstones or sedimentary rocks are forming on the surface, they have a little bit, and they have a little bit because the sandstone is being made from eroded granite and other rocks in the area get washed in and deposited. So they have a little bit, but the big numbers come from the granites,
Wow.
And things like the mantle, which should just take us back to deeper for a second, because all the melt has been extracted out of that early on by a rush of buses, as a peak hour, took it all out.
Yeah, keen peak.
Yeah, I can't handle you guys right now.
There's very little left. So when you see a really dark rock, and in Victoria, for example, we have lots of basalt rocks, which are very young, and they're coming from melting of mantle rocks largely. There's nothing to get on the bus. The bus is
it's already up
empty.
here. Yeah, exactly. The passengers are already up here.
Exactly. Those basalts have very low heat producing.
But throughout.
Yeah.
Sorry.
No. Please go.
Yeah. But lots of rocks. Australia is really special. It's one of the reasons I love Australian geology, because we have some really these high heat producing rocks that go pretty much all the way through the centre of the continent, over into Western Australia a little bit. But South Australia, Northern Territory, Queensland have lots and lots and lots of these rocks in there. And these extend into Antarctica because of when Australia and Antarctica used to be right up against one another, and some off into India and so on. So how they came about, we still don't know. And that was one of the questions that started me in geology in research, and I still don't know the answer.
So when you, because I was just going to say why.
That's the true. That's the true life of a researcher. We still don't know why.
So are you saying we don't know why these hot rocks are located where they are, and why they're not located somewhere else?
Yeah, exactly. That's what we're saying. And whether or not it's just preserved better in Australia, the central portion of Australia, or not. And what I mean by that is that the bus comes up, parks in the upper part of the crust. And then, as we know, over time, rain's going to come and wash it away. And maybe we just didn't have as much oomph up here, so it didn't rise as much and didn't get eroded. So we've kept it. That's one theory. Another theory is that we actually sampled a pretty cool bit of a big party down in the mantle where all the uranium and thorium was hanging out. They all got on the bus at once and just happened to pop up here. And we can't really differentiate those different possibilities still. One day.
Bummer.
But I know, it's so disappointing. But
did you have visions of starting a PhD of answering this grand
Absolutely, yes. I was going to solve it. I look back at some of my early abstracts I wrote for conferences, and I'm like, what was I thinking? How embarrassing to think that I could, answer these questions. But anyway, science is incremental, and each step is another step on the way, on the journey to finding out.
Fantastic.
Oh, goodness me.
Yeah.
I love how we just tracked, we started with heat, but I'm just noticing that we've gone from deep in the earth, and we've tracked these sort of elements that didn't enjoy being in the mantle. So they got into some melt, they came up to the surface. Then when they come to the surface, they do form things like granites. And that's sort of if you're not a geologist, I feel like that's quite a recognizable rock type. You slap a granite slab, or you can tap a Port Elliot. It's a recognizable rock. But then what happens when they erode is you have those same hot elements essentially coming into the sandstone, forming our beaches. Talk about a cycle, right?
Yeah, absolutely. And it's nothing to be, there's a very, very low amounts, incredibly low amounts.
Yeah, don't freak out. You don't need to worry.
Sure. Yeah, there's absolutely nothing to be concerned about. Yeah, exactly. So, and it's one of the things we can track and cycle through, particularly in this question of where did these granites come from? Are they just the same bits of uranium and thorium that have been processed multiple times into melt? So, yeah, lots of questions about that.
Heat, quite literally, is making the world go round. Yeah. And we can understand that all the landforms, our mountain, whatever, everything that's happening on the crust fundamentally comes down to the heat, to the earth just trying to shed its heat. But I feel like we're missing a big chunk in the middle, which is the mechanism of that heat. How does that heat actually change the crust? How does the crust work with that heat? And that's a T word, isn't it, guys? That's the T word, tectonics.
Tectonics.
Yes. Yeah.
We need a session on that.
I reckon so. I reckon Sandra's our woman for that too.
Please come back.
Oh, I'd love to. Yeah.
Thanks for the conversation, Sandra. This is it's a dream, isn't it?
It's a dream. Fantastic.
Thank you both. It's just so amazing, so much fun. It's lovely to chat with you.